Okay, everybody. Everyone's back. We'll start up again here. Let me share some slides. Okay, so I thought I would talk a bit more about some things that we can change in the run deck, and then Costas will pick up on a little bit after that. Okay, so these are related to what we call boundary condition files. For those that are interested. One of the things, of course, that people are always interested in changing is the topography of the world. So there is a topo line in the run deck where you change that file. Those are netcdf files. That's a kind of format that we use in most of the GCM community. Usually when you change the topography of the land, you also have to consider the topography of the ocean, because the topography includes the land sea mask. So if you want to use, say, an Archean Earth topography and land sea mask, in fact, of which we know very little, you can dream up one, or you can pull one from the literature that people think maybe some idea of what it used to look like back in the day. Then there's this RVR file. That's the river directions file. So this is a kind of a tricky file, in fact. So basically, you want to be able to tell the model where water runoff should take place. And this usually should be related to your topography, of course. So you want the rivers to run downhill in your topography down to the ocean grid cells, basically. So that's what this river directions file is. So I have some code that can automatically generate that from a given topography file if you need it for a particular reason. In Planet 2.0, we're hoping that some development in collaboration with the Earth modeling side of the house and the planetary side of the house at GISS will have a way to generate this automatically for us. So in Planet 2.0, hopefully we can get away from having to make customized river direction files, which is very tedious and time consuming if you don't have some code doing it for you. There is this name RVR file where river names come into play. That goes back to the heritage from the Earth model, where you could see what kind of river flows for a given name had, outflows, for example, into deltas and things like that. I say here there has to be at least one, but we have fixed that in the model, and that is no longer required. Then we have this thing called variable lakes. That's another very useful parameter. I say here you set to 0 for non-variable lakes, so they can expand and contract. So let's say, for example, you want to model a world that's, say, sort of like modern Mars, but does have a bit more precipitation. Let's say it's a bit warmer of a world, but you don't have oceans. So this is a nice feature the model has. So basically, if you have this variable lakes set to 1, so you allow lakes to contract or expand depending on the competition between the precipitation and the evaporation in a given grid cell. So we use this frequently in our desert type worlds or worlds with low amounts of water reservoirs on the surface that maybe don't include oceans, just lakes, for example. But of course, if you have oceans and you have lakes, then you can still use this. It's not required either way. If you need to generate new, or as I say here, remove ocean grid cells, then you also have to change the default ocean initial conditions file that Tony talked about a few slides ago. And as Tony said, he can give you some code if you decide you want to generate a new land sea mask, a new ocean with new ocean depths, and you need to generate an ocean initial conditions file with those new topographies associated with your new world. Then we have another important aspect of the run deck called the GL melt file. And this again needs to be changed if, as it says here, the land sea mask changes drastically. So this is kind of an old feature of the Earth parent model, where basically you can limit how much land ice you will allow the model to accumulate. So for example, on Mars, let's say you want to model ancient Mars. If you consider the height of the Tharsis region on Mars, you have surface water reservoirs and you don't have a dynamic ice sheet model, which we do not have in this model, basically all of the moisture on the planet will end up being trapped on top of Olympus Mons and the associated volcanoes at Tharsis. So this GL melt feature is related to another run deck parameter, which I have here, WSN max, which limits how much snow accumulation you can have. So it's kind of a fake way of saying, well, we shouldn't allow more than X meters to accumulate, and because we'll have some kind of dynamic ice sheets in reality, so that limits the amount of snow. And that snow accumulation that is not deposited there has to be put somewhere to conserve energy in the model. And those are dumped into ocean arrays, these GL melt arrays, which you place as masks somewhere over the oceans in your model. If your model doesn't have any oceans, of course, you can't use these GL melt arrays. It's not conserved. Although we have been making some changes that may allow other ways around this in Planet 2.0, but that's not quite defined yet. Okay. Then, of course, there's a whole slew of other things that should be of interest to you all, things like changing orbital parameters and other things. So the first thing that you have to consider if you're going to chase, for example, the mass of the planet, or the radius of the planet, the density, things of that nature, you'll have to create a new entry in a table, which I'll get to a bit later. And you'll have to give your planet some kind of name. So in the run deck parameter section, there is something called planet name. It's not hard to figure out what that means. You have to give it some kind of name like Proxima Centauri B, or TRAPPIST 1e, or name your favorite exoplanetary world, or ancient Earth version 12, whatever you want to call it. You'll have to use that name in the table a bit later. You can also set your eccentricity, of course. Shouldn't surprise you, your obliquity, and a whole bunch of things that are related to what we call the calendar. So things like, as you see here, your sidereal orbital period, your sidereal rotation period, and ways to, whether you should quantize your year length in integers or not. These are things that Tom Clune, who rewrote from scratch our calendaring system, will talk about tomorrow morning in depth. But he has offered us a lot of features, and he's done a really good job of comparing to the best theoretical models for what planetary installation should be like, for example, for different spin orbit periods, which you would also use these entries to generate. Now, another very important thing you'll want to do in the model is you might want to change what you would call your greenhouse gases. So we have a file called the GHG file. So there'll be an entry in the run deck parameter section where you say GHG equals a given file name. You'll have to give the path to that file name. And that, that particular file, as you see here, will contain the values in parts per million in your atmosphere of what you want the greenhouse gases to be. So that includes things like CH4, CO2, N2O, and also some other man-made greenhouse gases. So you can look at that file in your run deck. If you go to one of the two run decks that you've already hopefully built and looked at, if you look at the GHG file, you'll see where the path is, and you can look at that file and you can see how it's formatted and what the different greenhouse gases are that you can put in there. And as I said a little bit before, you can change, as I said, the physical properties of your world and the atmospheric mixture. So if you change, for example, how much CO2 you have versus CH4 versus N2 versus O2, then you need to make sure that you calculate what the mean molecular weight and the heat capacity of that atmosphere is. And that should be, as I say here, set explicitly in your model/shared/planet_params_mod.f90 file. And then that's where you'll see entries. You can look at that in the source code. You'll see entries for given planet names. The two that should be in there by default should be Earth, obviously, and one we call not Earth, which is kind of a placeholder. So you would copy the not Earth entries in this block section, repeat that, give it a new name, what you call planet name in your run deck, and then you will have to change things like the radius, the density of the world, the bulk density of the planet, sorry. And you will also want to change what the partial pressure of N2 is into the world, the partial pressure of of other guesses as well, which are defined in that file for you. And then, of course, the only thing else as you need, as I say here, is something that tells the planet how much insolation it receives. What's the incident amount of flux it's going to receive from the parent star that you're orbiting, and that's this parameter we called planet_S0. It's sort of a strange name, but it was one of those cases where we had something before called S0X for Earth applications. We wanted to make something a bit more explicit for planet. And that's more or less all you need if you want to change the insolation, but you want to use a solar spectrum, for example. So you just change that to how many watts per meter the planet's receiving at its orbital distance from that star. So for Earth, that's 1361. That's the value you would find by default in the model. Now, for example, if you don't change any of these things, then of course you'll get the Earth defaults. And if you're interested in seeing what the Earth default values are, or if you've changed things and you want to see if the model has picked up things as you expect them to be, then in that first hour that the model runs, when you first start the model up, there'll be a file generated in the run directory called runid.prt, which you should see again if you've already successfully completed those 2 simulations we asked you to start up. And in there you will find the values for all of these quantities in the run deck. Now, that GHD file, as I said, you can put the values in parts per million, but let's say that you have a GHD file, but you don't want to bother changing it, but you don't want any CH4 in the file, or you want to double the amount of CO2 in the file. So you can also, in the run deck, set these things called CH4X, CO2X, NO2, N2OX, etc. So let's say you want to have 0 CH4, even though it's defined as, say, 1 parts per million in the GHD file, you can set CH4X equal to 0. It will override what's in the GHD file. Let's say the GHD file had a 400 parts per million. You're doing a series of simulations of different parameter runs, and you want to double the CO2 for a series of different run decks. You can just set CO2X equal to 2 to get 800 if your default in the GHD file is 400, etc., etc. It's a little complicated probably now, but you'll get the hang of it as you play around with the model a bit more. Okay, so another thing we have is a single column model. So as I pointed out in the beginning, the model has a large number of columns. It's a 4x5 model, so it's got 46 latitude coordinates and 72 longitude coordinates, basically, centers of these cells. But it is possible to run the model in a 1D model, in a 1D mode. We have it working in kind of a beta mode for Planet 1.0, and we were hoping to also make it available in Planet 2.0. But to be honest, we have had basically almost no requests for this to work. I mean, the advantage of using the 1D model, of course, is that it runs very quickly. So you can do large parameter sweeps with a 1D model version of ROCKE-3D, which could be nice. It can run on your laptop because it only needs 1 core to run the model in this sense. So if we get more demand, probably we would make more effort to make it available. But currently we just have kind of a beta release for Planet 1.0 that I've had running for a couple of years, but I frankly have not used it myself very much in recent times. I just haven't had much need for it. But if there is a demand from the community to run the 1D model, we probably would make more effort to make it available. It's not too difficult to get it working. Okay, so of course, what you've heard many times now is that the model will crash under any given number of circumstances. The model got too hot because your star was too hot or too close to the planet, or your planet was too far away and your ocean froze to the bottom, or you're pushing the model in ways that it is far outside what the typical Earth model had been run at. And there's still some checks in the model to make sure things don't get too out of bounds. That's often what the crashes are that we find are. They are bounds that were put in the model to protect you from doing things that are outside the physics of the model. So let's say you don't want your wings to become relativistic in speed, for example, on your planet. So there is this Google document link, which you can click and take a look at. And these are solutions to various crashes that we have seen. Sometimes there's nothing you can do. For example, if you get what we call a small MO crash, that means your ocean in a single grid cell has probably frozen to the bottom, and there's not much you can do at that stage. You have to rethink your boundary condition files and restart the model from scratch, unfortunately. But other things are usually involved with changing the dynamical time step of the model, for example. So often we find that by making the dynamical time step smaller, we reduce the number of these instabilities in the model, and the model can keep marching forward, which can be very useful. So it may run a factor of 2 slower or a factor of 4 slower, but if you're near the end of what you think the model is, if you think the model is approaching equilibrium toward the end, then it may be worthwhile for you to consider just changing the dynamical time step and keep the model marching forward. So take a look at those if you have problems with the model crashing. Okay, so I'm going to stop there, and I'm going to let Costas take over from this stage forward. So Costas, are you around?
I'm here.
Okay, great.
Okay, so let's discuss a little bit about model output, both the output that the model is generating while it's running and some restart files, and also the output that you are actually expecting to see, you know, all the things that you will be plotting. So Mike mentioned this runid.prt file, which is essentially whatever the model is printing when you put a print star statement in Fortran. And it does print a little bit more on that, but essentially you need to think of this file as the standard output. So if you put a simple print statement somewhere, this is where it will show up. It's pretty long, and it contains useful information. It contains some stuff about the model state at the beginning, like we discussed already a couple of times about the calendar. So it tells you how many days every month has and stuff like that, or how long is the day in seconds. It contains really a lot of information about the model that is currently running, and then it updates itself as the model is running. And then we have a lot of files that are called with this strange word I have there. So MON is the month in a 3-day abbreviation. So Jan for January, Feb for February, etc. Then it is a 4-year digit for the year, and it can add leading zeros if the number is less than 1,000. But you need to remember to use this flag that we discussed earlier, and Mike put on the chat window if you need a year that exceeds 10,000. Then there is this ZZZ part of the file name after the dot that the model is saving primarily, let's say, an accumulation file. So this accumulation file is called ACC. The ACC is the part that goes into the Z here, and stands for accumulation, obviously, and it is essentially all the model output that you will be looking at. And then it is the runid.nc. Now, the accumulation file with this ACC contains a lot of, is not ready to be used. It is written in a strange way for good reasons. But the important point is that it contains several other files, and you need to scale it first to allow so that you can get those other files. So you run a command, it is called scale ACC, and then it will give you more files, so more flavors of the exact same naming, and only the ZZZ here in the middle will change to something else. I'll get to that in the next slide. Then we have the RSF files, RSSF Restart file. And the default is to save them, I think, every month. But these are really large files because they contain the full model state in in double precision. So you can have a binary accurate restart every time. So you can control how often to save those things by using the KRSF flag in the RunDeck. It's somewhere at the very end of it. So if you say KRSF equals 12, then it will be saving every January 1st. If you will say KRSF equals 1, it will be saving every month. If you say 120, it will be saving every 10 years. And given the calendar that every planet has. So this file is useful for restarting the model from any point during the simulation. So if you have a simulation that lasted, say, 1,000 years, and for whatever reason you lost one file somewhere in the middle, so you can go back to those RSF files, restart the model from that point, run over the period of the missing files, and then there you go, you have them again. It's you can also use it to eliminate the need to have a spin up in every simulation. So if you have, for example, a planet that is very different from what your current initial states, the current initial states that exist either in your repository or in our repository, and you need something completely new, you run one simulation with this new configuration for a long time to equilibrate, and then you use the RSF file to run any sensitivity studies on that planet, starting out from there. So if you are doing sensitivities for the atmospheric composition, for example, you don't have to reinitialize everything and and wait for the ocean to equilibrate for every case. You do it for one, and then you branch out from a fairly equilibrated state. And then, of course, you will need more time to equilibrate with the new conditions. It's not that immediately the model works, but chances are that whatever you are doing is small enough compared to the initial out of equilibrium state that you started the model from. Then we have some files that are called fort.1.nc and fort.2.nc. And these are restart files, very similar, but not exactly identical with the RSF files. The key difference between those two types of files is their functionality. The RSF file gets named based on the timestamp of when it was written, of which time it represents. And this is unique in every simulation, and it survives forever until you delete it. The Fort files are essentially RSF files with very small differences, but they alternate between writing. So the model first writes, when the model starts, it immediately, it reads the initial conditions and then saves the fort.1 file that contains the model state with initial conditions alone and nothing else being run. Then the model runs for the setup hour that we said that usually lasts an hour, which is 2 time steps. And then at the end of it saves the fort.2 file. So you have 2 different states of the model that are a little bit apart. When you start the model again, to continue this simulation all the way to the number of years you wanted, the model checks those 2 files and says which one is the most recent. And then it picks that one as the place where it needs to start. So it reads fort.2 in this case and continues the simulation. Then we have a flag in a parameter in the RunDeck called nDisk that I think the default is 960. So this means how many time steps the model needs to take before writing this Fort file again on disk. And 960 time steps for the Earth configuration means 20 days. So every 20 simulation days, the model will be writing those Fort files. And the way it does it is that it goes again, checks which one is the newest file, does not touch it, and overwrites the old one. So the first time this happens, the fort.1 file will be overwritten, and then immediately it becomes the newest one. So 20 days later, fork.2 will be overwritten because now it's old. And then 20 days further later, fork.1 will be overwritten. And then you keep alternating like this. The reason why we do that is because sometimes something might happen, you know, an electricity failure or whatever, some file system problem. For whatever reason, the model might crash. And this is the way to keep the state of the model fairly up to date, and then don't have to continue to start the simulation from the beginning or from the most recent RSSF file, but instead only lose n disk number of time steps. And we have two files so that we get protected from the case that the model crashes during writing of those forked files, and then this becomes corrupt. So if something like this happens, let's say fork.2 became corrupt, then the model cannot start from that, it will keep crashing. You delete fork.2, overwrite fork.1, copy fork.1 into fork.2, so you have two files which are exactly identical with a different file name. The model checks, sees the same date, picks one at random, and continues from there. You just need to make sure that you are deleting the corrupt file and not the proper file. Then we have, so then the ACC file that I mentioned earlier, the accumulation file, you can control whether you save that or not with the kcopy flag in the rundeck. Kcopy equals 0 says don't save it, which is kind of a weird choice because then you have no output. And then equals 1 says, which is the default, saves it. You change that with the scale ACC command. So you type scale ACC, the file, the ACC file you want to scale, and then which files you want generated out of the ACC file. And I'll get to those in the next slide. You can also use the sum files command. So this combines accumulation files into bigger accumulations. So if you want an annual mean, you can say sum files and then list the 12 accumulation files of the individual months, either by using wildcards carefully or by simply listing the files one after the other. And then the sum files is smart enough to create a file name that makes sense based on what you have been using what they have been averaging through the command line. Both of those utilities exist on your computers because you compiled them when you did the make diags at some point during our instructions. So you can go into that directory and find them there, the executables. You can soft link them or copy them to some place that it's inside your path, or you can put that directory inside your path any way you like. We also have diff report, which is a utility that is very convenient in comparing files. So let's say you're running two simulations and that you made some development, and that development is structural rather than substance. So the results should not change. So you run the model for a month. Let's say you take a January file, and then you compare the two files with diff report, and it tells you whether those files differ. You cannot do that with plain diff, because the diff command sees that these files are binary and checks them for binary, whether they are binary identical. And they will not be binary identical because the metadata in the files are different because they come from different simulations. So diff report was created to compare the actual numbers in the files instead of just the metadata that are being ignored. So after you run scale, and then the scale ACC command can also be run in the output of the sum files command, because the sum files, if you create an annual mean file, it will create an annual mean ACC, and then you run scale ACC on that. Sounds complicated, but it's really nothing. You get used to it on day one when you start working with model output. So you can see the netcdf files with any way you like. Panoply is an in-house tool that we have that is we keep developing, and it's nice that it is extremely capable. It creates publication quality figures. It's really nice, and I'm not going to cover that. There's a website you can download and use it if not already. And a nice thing is that this is under active development. So if you'll find any bugs, or if you have any feature requests, you can contact the author, which is listed under this website. And chances are you will get lucky and you will get it, unless you're asking for something really outrageous. And then a trivial, something very basic is NCView as well. Probably you're already using that. If you're an HDF user, you know how basic it is, but it is super fast over remote connections. It's the fastest way to see an HDF file if that file is not sitting on your computer. Let's go to the next one, Mike. So Scale ACC. Here are a list of common files that you can generate. So you say Scale ACC, the ACC file you want to scale, and then one of those abbreviations, AIJ, AJ, AJL, etc. These are the most commonly used, and you have to find out which variables exist in each one of them to really know, but chances are that you will be using AIJ. And this is a two-dimensional file that contains longitude and latitude dimensions and atmospheric components. So A for atmosphere, I for longitude, J for latitude. So by saying that alone, you understand that AJ is longitudinally averaged variables. So this file contains the atmospheric variables that are the mean over longitudes for every latitude. And then we have the AJL, L for height, so for layers. And you get the same thing with AIJ, but in this case, it is a two-dimensional array, which is the average of three-dimensional arrays. And you also have the AIJL a little bit further down, which is three-dimensional output. You have the O, which is the ocean, and so equivalent naming, and it gets pretty intuitive, as you can see. AGC is some general circulation variables that you might find useful there. And can you go to the next one? So this is the additional files on top of the previous slide, and that you can also see what they have. Whichever starts with T means that it has tracers in it, so it contains some prognostic tracers. Whether they are passive or they are really affecting the climate is irrelevant. The fact that they are prognostically calculated means that this T file will exist. And if you want all of them, in case you want to see what they are, for example, you say Scale ACC, the ACC file, and all, as you see at the very last bullet. But as I said, the one file that you will be using overwhelmingly more than any other is the AIJ file. Yeah, I don't think I want to go any further in here. So let's go to the next one. So the source code structure. At the very beginning of the run deck, you will notice that there are some lines that they start with a hash define. And then they have a word which can be cryptic or can be descriptive. These are C preprocessor options that are used in the model. So before the model compiles, it runs the C preprocessor, and based on those instructions that it finds in the run deck, it parses the file, the Fortran files, executes the preprocessing by removing the pieces that are not needed and keeping the pieces that are needed, and then compiles that file. Everything happens on the fly for you. You don't have to worry about that. The important thing is that for this to happen, you need to have this line that is listed in the first bullet in the Fortran files. If you do not have it, then the C preprocessing options in the run deck are being ignored. And you don't have to worry about that in the files that you already have, but you need to remember that if you are creating new files yourself, and when you're doing some development. And also you need to worry about the extremely few files that they don't need to have it, but if you will modify and then add some options like these, then you will need it. Anyway, it is chances are that you will never have to worry about that, because very few people really create new files. They usually modify existing files, and in the vast majority of the files this line exists. So everything happens under the hood for you. Then we have files that are appended with _com and _drv. This is not very consistent in the model, but it is, as a rule of thumb, you can remember that. In essence, if you have some functionality in the model that is called XXX here, it can be, I don't know, atmospheric dynamics, for example, ATM dyne is the file name. So the atmospheric dynamics file needs to have some variables and parameters that it owns. And essentially it is the module that contains the variables that the atmospheric dynamics is using. So this is typically saved into the _com file. And then when you do use the atmospheric dynamics module, that module exists into that XXX atmospheric dynamics _com file. And so the com file contains the variables that the component is, that this piece of the model is owning. The file with no appendix, no prefix is having the actual calculations, and then the suffix, I'm sorry, and then the suffix of _drv contains the link of that piece of code with the rest of the model. So any subroutines that are being called from the main file are being called from the driver file. As said, it's not 100% consistent that way, but if you are doing any development, you should try to respect that structure, even if you will not be able to see it throughout the model. Two important files that are inside the shared subdirectory are the constants mod and the planet params mod. Mike already mentioned the planet params mod. This is where you go and define any new planet that you are having, or if you want to go see what the values are for the current planets that exist. And the constants mod is exactly what it says. It defines certain physical constants like the Avogadro number or the, whatever, the gravity. No, the gravity goes into the planet parameters. Any physical constants that are truly constant are defined in there. And another important file to keep in mind is the defacc.f, which is define accumulation diagnostics. So if you want something from the model and it is not in the output, then you need to define it in that file. And there are ample examples in there on how to do that. And then you need to populate what you defined in whichever part of the model is relevant. And there are examples on that. Chances are that if you want to do it, you will probably need some help from us for your first one. So you need to, or the other way to do it is you need to think which variable resembles what you are doing. If, for example, you want to output the temperature at the 5th layer, you can see how the temperature at surface is being added and make small change, replicate that, and then make small changes to go into layer 5. I can think of nearly no cases where there is no proper example already in the code that you can follow. I think that's it.
I think you're right for today. See, I should just mention as an aside that if you haven't already realized it, this model produces tremendous amounts of diagnostics already. In fact, it's considered one of the strengths of our model that if we haven't already put it in there, I'd be surprised. But of course, it does happen sometimes. But probably you can find it if you know where to look for it. So often it's a question of just, if you don't see it in the AIJ file or some of the other ones we mentioned, you can write us and we can tell you, oh, it's probably like if you want the stream function, that's in the AGC file, for example. If you want to look at ocean dynamics, as Costas said, you look in these OJ or OIJ files. So it's a bit intuitive in that sense, but the model has a tremendous amount of diagnostics, and it does create some overhead, of course, as you might imagine, creating all these diagnostics. And that kind of goes back to something that I thought I should mention that Tony mentioned, this NDisk parameter, where these fort files are written out X number of time steps. So you might want to consider, like, let's say you're running on a small supercomputer and you're running 10 jobs. You might want to make this NDisk number a bit larger, 2 or 3 times the default, so it's not spending huge amounts of time writing out these fort files more than it needs to. We recently had this problem on our own supercomputer at Goddard, where we were recommended to at least double that value because the I/O on our main file system was being overwhelmed. Go ahead, Costas, you had something to say.
Yeah, so the important question to ask and how to get this number right is how many days or hours of your world time you are willing to lose if something goes wrong.
Yes, exactly. So if it's every 20 days and the model bombs or the file system crashes or the electricity goes out, you have to consider that you only have to restart it every 20 days. But let's say you set it for 20 months or 100 years, you might have to wait a little while to get back to where you were. And that goes back to also to this KRSF command that Costas mentioned. It's the same kind of principle there. If you write out these checkpoint restart files, these RSF files, again, according to what you think you might need, because you might want to restart the model for another run at a different point as the model is reaching equilibrium, for example. So some people set this KRSF to be, say, 100 model years or 10 model years. It just depends on what your needs are. So think about what you want to do and how often you might want to run that file out. And I should say, it has happened to me very infrequently, but it has happened once or twice where both the fort files were corrupted by some strange quirk, probably my fault, who knows. But I did have the RSF file, so I could go back, and I was, in that particular run, I was writing those out every 10 years. So I only lost 10 years because it was kind of before the next one was about to be written. That's not bad if you have a run that's been running for a few thousand years, for example. So think about those things. Okay, so we're at the time for another break. So we'll take a 15-minute break and we'll start at the top of the hour again. And then this last part, we'll spend up to an hour. It just depends on you, on any questions you have about the materials we've presented today. If we get questions that are related to material tomorrow, we'll defer those to tomorrow. Otherwise, think about the kind of questions you have about the model and what you might be interested in learning more about. We'll be happy to fill you in.
And it's a good idea to start playing with your run deck. Create 2 run decks, one for the QFlux, one for the ocean. Make a diff, run them for the setup hour, and all those things that we discussed here, practice them today. Otherwise they will not stick.
Yes, and tomorrow, actually, Chris Kalos will spend the last hour of tomorrow's tutorial showing how to create a completely new run deck. So he has a tutorial section just for that. So you can also gain, hopefully, quite a bit from what he'll present tomorrow in that sense. Okay, so we'll take 15 minutes, and then Costas, myself, Tony, and Igor, and Eric Wolf is also around. Hopefully we'll be around to ask any questions you have about today's material. Okay, see you in 15 minutes or so.